So yeah, we're going to focus on the end user design. Oh, I'm sorry, first slide, that's who we are and why you care about us. And so part of this trip as well, Nikki and I are going to be traveling across the entire island. We're going to be in 11 cities in 26 days, meeting people from universities, from prosthetic and orthotic centers, hospitals, manufacturers, and such. And we're trying to find ways to connect with people, to connect on projects. And this can be small projects like, bachelor's theses or master's theses, and this can be big things like grants as well. So keep this in mind, because this is what we're looking to do on this trip, is make connections for this. And yeah, I'll hand it off to Nikki to say a bit about herself and what she does.
Okay, so just to start off, I'm going to talk through the main 3 types of prosthetics, because I do a little bit of work across all 3 different types. So the first kind is just the powered, so the passive prostheses. So these can be cosmetic, or they can also be functional, but they only carry out one type of action. So for this, I work with a company in the UK, it's a fairly new company called Koala, and they do soft shell prosthetics. So with this, we can design attachments to put on the end in order to be able to carry out certain activities. And I'll show you some of those in a moment. The other kind is body-powered prostheses. So I work a bit on these to design or improve the design of them and increase the functionality, and therefore the user's comfortableness with using it. So sometimes they may have a body-powered prosthesis, but it's heavy, it's warm, doesn't behave how they want it to behave, and so they abandon it. So it's how can we take into account the user's needs and also manage their expectations so that when they use their prosthesis, they're happy and it functions as they want it to. And lastly is my electric prosthetics, so the bionic hands. So this is the part that I find quite exciting, and I do a lot with the control, the design, and also making sure that users' expectations can be met. So just to give a brief overview, so some of you may know this already, but the rejection rates for upper limb prosthetics are very high. So it's different across the world, but it's roughly around 40% average. And even though there are advancements in upper limb prostheses, there's not been a significant amount of change in the abandonment rate. So obviously the user needs are not being met by the prostheses that are accessible to people with a limb difference at the moment. So what I do is I work with users to understand their needs. So I've just started working with users, whereas Mike's been using with them for a long time. So we want to really understand what do they want, why their current prostheses don't actually meet their needs. And from this, we can come to the design specification and create a new prosthetic. So as I say, I work in 2 different types. So for the body-powered prostheses, the main things that we're focusing on is a new terminal device. So is a split hook still the best option? Could we have something that looks more like a hand? So it's a cross between a body-powered prostheses with a split hook and the cosmetic prostheses. So it's got some functionality, but it doesn't have everything because it's not what some people may want. We're looking at including a wrist unit. So at the moment, we can have pronate, supinate. So we can have the rotation of the hand. So these are quite common in the UK. But what we don't have is the flexion and extension. So trying to incorporate this in a very compact setting and low weight, so it's comfortable for the user to wear, and they can get this increased functionality. And also looking at the harness and actuation system. So I'll show you in just a moment a photo of how the harnesses sit on the body, but they're very uncomfortable, and they can actually rip clothes and the skin. So if you wear your prosthesis for a long time, it is quite uncomfortable. And with my electric prostheses, even though we want these to carry out a similar function, they do have a different requirement from users. And the main thing is that they're lightweight and comfortable. So because you have to have your battery in your electric prostheses, obviously it gets very heavy. And again, the affordability, because it's very complex, there's lots of research and design that's gone into it. But we still want it to be high functional with this affordability and also reliable. So just to give you some ideas, so this has all been done by my students, so either undergraduate students or also some PhD students. So what we looked at with this is adding a flexion extension to the wrist unit. And we started off looking at having this just body powered. And so we came up with a design that's compact, lightweight, so this is 3D printed with carbon fiber to make it robust, and seeing how this can actually function. So what we can do is put a split hook onto the end of this. And with this, we can have the extra degree of freedom. So if somebody's reaching into a cupboard, if it's on the top shelf or the lower shelf, they may need to have a different wrist motion. So it's basically how do we incorporate this into the design so it's lightweight and can give the increased ability to the user. And as I mentioned before about the harness system, so this is a photograph of somebody who has both arms amputated. So they have to wear 2 prostheses on either side. And you can see that the webbing on the bottom left is very complex. And the material is really rough, and it has to be robust and strong in order to allow the power to translate to the split hook. But as I say, it can rip clothing, and it's even ripped the skin before. So it's just very uncomfortable to use. And if we're in a climate like we are today, where it's very hot, it's going to be extra uncomfortable. So what I had a student doing is looking at the design of this, so it can have a soft material, a strong material, flexible, so it moves as it does with normal clothing. And it's also minimal coverage, so we don't have a lot of increased heat. And we gave this to a user, they tried it on, and they really liked it. They said it doesn't impact their movement, it feels like they're not really wearing anything, but it would still allow that power to be translated from their body into the prostheses. So I'm just going to show you a little bit about the myoelectric prosthesis design. So I haven't put everything in this because some of it we are trying to commercialize and go through the protection of the design process. But these are some either very early or very new designs. And basically this is a new approach to a hand. So none of these have any traditional joints in them. They're what we call flexure coupling. So we're using the elastic properties of the material in order for it to bend. And we're using a tendon-based system to get the finger to bend. So we attach the string to the end of a finger. So for example, in this finger here, we'd attach the string right to the end, feed it through all the different parts and onto a motor at the bottom. So these fingers are under-actuated, but this means that it can grasp lots of different objects. So it can grasp something quite heavy and bulky like a can, also it can hold something quite small like a pencil or a toothbrush. And we can hold these in different ways that traditional prostheses can't because of the under-actuation of the hand and the fingers. So to minimize the weight, we don't actually have a motor for every finger in the thumb. So what we do is we drive the last 3 fingers together, the first finger alone, and the thumb is driven by a single motor. And we can also move the thumb around passively. And we found that we've been able to put this into a light, compact weight. So the mass of the hand itself is under 400 grams, so it's very light. And we put this onto the end of a socket, given it to a user, and they've actually been able to pick up objects such as an apple and a lemon, but that's about the weight of it. So some of the challenges that we still have is how do we increase the force in this to make it more applicable to everyday objects as well. And over on the right-hand side, so this is from one of my PhD students, Nikos, who is looking at basically making the design more simple and easy to manufacture. So as you can see on the left, we have lots of screws, lots of individual parts, and it's quite a complex design. But on the right, what we have is everything is 3D printed, and if you wanted, you could print this all as a single piece. So at the moment, it's multiple pieces just because it's going through the design process. And what we have is we have, again, these flexible joints that are under-actuated, and we also have some webbing over the inside of the joint to prevent things getting trapped. And at the moment, this is just lab-based. We have a motor for each finger and 2 motors for the thumb. And we can see that if I play this video, the motions that we can have. So it's not playing as clearly as it was just before. But basically, we can describe any grip pattern that we want. So we can have any of the different 21 common grip patterns in order to do the different objects. And some of the other work that I've been doing at the moment and have a grant for is looking at how we can use computer vision in order to select the grip patterns. So at the moment, if you have commercial prosthesis, you have to change the grip pattern manually. So either you push a button on the back of the hand, you have to cycle through them all, which can take a very long time and users get frustrated. So they tend to keep it on just one grip pattern. But what we hope to do is be able to use a camera in order to detect the object is going to be picked up, and then using our algorithm, we can say, well, this is the hand grip we need in order to pick this object, and as you go to pick it up, it'll select that hand grip, and we'll be able to pick the object up quite easily. In that sense, we should have a very fast response time from the user deciding, I want to pick an object up and grasping it. Instead of at the moment, they have to cycle through, they have to align all their angles and pick it up. So basically, we're trying to get as close to the human reaction time as possible. And also, just a bit of fun research that I do on the side with some of my students is designing prostheses for certain applications. So on the left-hand side here, we have Alex Lewis, who is doing a rowing challenge in rowing the south coast of the UK. And he contacted me saying, I've never sat in a rowing boat, but I want to row the south coast. So I was like, great, let's design something. And we actually designed both the right and left arm and to enable him to attach to an oar and get enough power through to be able to do the row. And he went out on the sea and it worked really quite well. So things like this is a little projects that I really enjoy. And on the right hand side here, again, fly fishing was something that he really liked to do before he lost his limbs. And so what we did is designed a very simple system in order to allow him to fly fish. He'd casted about 5 times, and as you can see, sort of in the video, he actually got a fish on the line, but didn't actually manage to land it. So a lot of my research is based on the principle of what do users want, how can we make this happen, and then designing something and testing it with them to see if it actually meets what they need and their expectations. So another small part of research I've been looking at is looking at how we can monitor the residual limbs. So with prostheses and socket fit, it's really important that this is a good fit and it's very comfortable for the user. However, there are points within the socket that might have pressure points and can cause irritation over time. So one thing we want to do is actually monitor how the residual limb is over time. Is there any fluctuations in volume? And therefore, to do this, what we can do is try and use technology that everybody has in their home in order to create a scan of the residual limb, and therefore we can see how the limb is behaving over time. So what we looked at is basically trying to use our smartphones to take photos or scans of our residual limb and see how well we can actually capture the limb itself. So what we did is we went onto the App Store and Google Play and looked at what applications there are on there. So everything we've used in here is commercially available. Most of them are free. It's only one that you have to pay a small amount for. And we used a very expensive 3D scanner as our criteria to ensure or to measure how well we actually could capture the residual limb geometry by using the smartphone applications. The first thing we did is we just took a plastic cast of a residual limb, put it in different environments, and saw if something static in different environments of the similar shape and size that we want to capture, how well does it behave? And we saw that actually this behaved very well. The environment didn't matter too much as long as there's not too much shadow. So the main key thing is avoiding shadows when we're doing the scanning. Then we moved on to live patients and live scanning. And so we scanned 10 different people with different levels of amputation. And these are a sample of the results that we got. So the top left results, the RTEP, so this is our criteria. So this is a very expensive high-end scanner we would expect to be able to capture shape and volume very well. And the other ones around it are the ones that we captured either using just photographs and doing some photogrammetry on it, or by using the apps on the phone itself. And as you can see, 2 of them, so Polycam and Luma, performed pretty well. So Polycam, you can see you get the shape pretty well, it's a pretty smooth surface, whereas Luma, the surface isn't captured quite as well. But we want to see actually, can this be used in a clinical environment? Is it good enough? So we did some analysis on it, and what we actually found out is that the coefficient that we're measuring exceeded the level that we needed for it to be used in clinical practice. So the level for clinical purposes has to be over 0.9, and for some of them we were getting 0.99. So this means that we can actually capture the residual limb accurately enough for this to be used in clinical practices. So as I say, this is a very small sample size that we were looking at in a controlled environment. So we want to extend this to different environments, looking at different skin tones, looking at different climates, and seeing how this affects the results, and if we're still able to take this into clinical environments. So that was just a brief overview of the work that I've done in the area of prosthetics. Ranges quite a bit, but basically I want to continue these projects into the future, still working with users and clinicians to try and work out what their needs are, and then how we can answer these using our engineering knowledge. So I've talked for long enough now, so I'll pass it over to Mike to talk about his work.
Thanks so much, Nikki. And so for those of you who don't know me, which I assume most of you don't, I'm half anthropologist, half engineer. So as an anthropologist, I'm really interested in people's biology and culture and how that changes. And I try to combine the two of them in I created my own word for this. I say I'm an anthro-engineer. And so a lot of what I'm focusing on here is the end user design. So I spent about 5 years trying to understand how we can better help the end user and get products that fit them better. So whereas Nikki focused on the upper limb, I focus on the lower limb. And there's about 31.6 million lower limb amputees worldwide, and the vast majority of them live in low and middle income countries. Now, what's really interesting about that is most prosthetics, if not all prosthetics, are designed by high-income countries. There's a bit of a discrepancy there, right? And unfortunately, the people that design prosthetics for low and middle-income countries often do not go to these places to figure out what the end users need, or they go to 1 or 2 countries and make generalizations about all of them. This becomes problematic because within the UK, if you lost your foot, there'd be over 20 different prosthetic feet that your prosthetist helps you decide what the best one for you is. Yet the idea that there's no difference between user needs in Cambodia, Sri Lanka, and Tanzania is ridiculous. That variation exists within the UK, but not between countries. So for this project, I've really just been focusing on figuring out the end user needs and how they vary, or basically how they differ. And I focused on northern Sri Lanka for the last 5 years, in particular the Jaffna area. And we use 4 different approaches for this. We use first published data, then we use local prosthetic and orthotic, or P&O records, and then we use broken prosthetics and field work to better understand prosthetic design, in particular prosthetic foot design. So to do the global database analysis with the published data, we did a literature review of published amputee data in countries that were involved in conflicts that resulted in at least 25,000 deaths since World War II. So we had to have some criteria. And wars, especially wars that end in a lot of death, tend to have a large amputee population. And in particular, they tend to have a large lower limb amputee population. So we found 103 journal articles or published data sets, and this could be white papers, so like the Red Cross publishes a lot of this stuff, or it could be governmental data, and we wanted to see what we could learn from it. So we used some machine learning techniques to see if we could learn more about the demographics of the people that we were dealing with. So were these people younger, were they older, how that correlated to type of amputation, years since amputation. But what we found is that everyone reports data differently. There's no one standard way of reporting this data. And because of that, it became very difficult to compare. So one data set might have a lot about age and demographics. Another one might have a lot about sex and cause of amputation. And because of that, when we combined everything, there was lots of missing data. And that led to very low accuracy in our machine learning models. But we were able to learn some things. Almost all these studies reported on the type of amputation and the cause of amputation. So in these graphs, you see it going from 0 to 100%, where we basically took all the numbers and we divided it by the total to normalize it to 100%. The red represents high-income countries, whereas the purple, there's only a little bit of purple, is upper middle income, and the blue and the green are lower middle income and lower income. And so it's mostly LMIC. Lower middle income countries. And what you can see is proportionately, there's a lot higher proportion of lower limb amputees in high income countries, and a relatively higher portion of upper limb amputees in LMICs. And we think this is related to the cause of amputation. If you see, the 2 main causes of amputation in high income countries are diabetes and accident or trauma, so people getting in car accidents. Diabetic amputees tend to be lower limb amputees, and that shows the high proportion of lower limb amputees in the high income countries. Whereas if you look at the cause of amputation in LMICs, we have weapons, medical, war, transport, industrial, animal, and farm. And these lead to both lower and upper limb amputees. So I remember talking to a group in Kandy, Handicapped International, and they talked about how their upper limb amputees would come from these machines that would process the husks of coconuts, where people would get their arms caught in them, and that would either lead to a partial hand or upper limb amputation, whereas these injuries aren't as common in high-income countries. But even so, the proportion of upper limb amputees around the world is relatively low, or only about 10 to 15% are upper limb amputees. So that's why we focus on lower limb. And if you look at the type of lower limb, it's HD is hip disarticulation, then we have transfemoral knee disarticulation, transtibial, and then partial foot or ankle disarticulation. And partial foot and ankle disarticulation almost only exists in high-income countries, and this is again related to diabetes. You have an ulcer, part of your foot is taken off, whereas in LMICs, it tends to be more than part of your foot that's taken off. So if we're looking at lower limb amputees and LMICs, the one thing that they all have in common is that they all use whole feet. Some of them might have a pylon, some of them might have an ankle joint, some of them might have a knee joint, but all of them are going to need feet. And so we decided to focus on the feet. And the other thing about this is the cause of amputation. People who have diabetic amputations, there's a 50% chance you're going to be dead within 3 years. And that's because diabetes has ravaged the inside of your body at that point in time. So diabetic amputees tend to be older and towards the end of their life, so being comfortable is more important to them. Whereas people who have war amputees, for example, tend to be younger and they want to be more active, and they live decades with the amputation. So since these weapon, war, medical transport amputees are higher in LMICs, we figured we wanted to have more active prosthetics as well, because it's probably a younger cohort we're going to be dealing with. So then I've been working with the Jaffna Jaipur Center for Disability Rehabilitation, the JJCDR. It's the primary provider of prosthetic and orthotic services in the Jaffna Peninsula for over 30 years, and has a digital database with 30,665 unique patients registered to it. Now, this doesn't mean 3,665 unique individuals, because sometimes people are duplicated, but unique records. And that was from 1986 to 2018 when we got this data set. And it was about 2,500 males and about 1,000 females in this data set. So what we did is we worked with them to analyze this data to see what we could learn about the local amputee population. And if you look at the age of amputation, it tends to be quite young. The mouse is coming up. These high bars over here is about, the 16 to 22-year-old range. So people within this age range are going to be living many, many years with amputation. And if you look at the cause of amputation, the two main causes are shell blast and landmines. So these are war related. And that accounts for over 50% of the amputees that they see in this center. The next main cause was diabetes, which was actually surprising to us, because while diabetic amputations are on the rise in high-income countries, when we talked to people up there, they didn't think that diabetes was actually a main cause of amputation. And then the next one was road traffic accident. And so these four main causes of amputation account for 80% of the amputees in the north. If we just, they don't give upper limb prosthetics anymore, so they only had about less than 200 upper limb amputees in their database. This doesn't mean there's only 200 upper limb amputees, because obviously if they're not giving prosthetics, then the upper limb amputees aren't going to be going there. But there was 2,364 lower limb amputees in their data set, and most of them were transtibial. And this is consistent with what we see with landmine and shell blast amputations and diabetic amputations. We looked at the four main causes of amputation and how they changed through time to see what the amputee population was going to be becoming as we moved forward. You can see landmine-based amputations after the war finished. There was still some that were going on. That's because of leftover mines in the ground. Shell blast was very high at the end of the war, but then dropped down. You still see a couple after the war ended, but I think those are landmine amputations that are improperly coded in the database, which is just one of the things. These databases are imperfect, but they tell you a lot of useful information. What was particularly interesting is road traffic accidents. It's just as, even though it looks like it might be increasing, it's just as common now as it once was. And then you see the opposite happening in Cambodia, whereas road traffic accidents are on the rise, and the same in Tanzania. And this is because of cheap motorcycles from China that are coming in. And when people get in accidents with a car, they get a crush injury, which leads to amputation. Now, if you're in the same accident, but you're in a car, you just have a clean fracture, and so you can keep your leg. But with motorbikes, it often leads to amputation. So that doesn't seem to be as big of a problem in the north, whereas it is in some of these other LMICs. What was really interesting for us is the diabetic amputations, which you can see there's a clear positive trend with time, and it's going up pretty quickly. They didn't know this was happening in the north. And so we were able to talk to some of the surgeons that are at the Japanese teaching hospital about this, and we were able to talk to some of the people there, so that just make them aware. And we published this data last year, which is open access, so anyone can go and read about it. And then we ran some advanced statistical models, which we haven't published on, but what we found is people with war-related amputations were less likely to get devices repaired or adjusted and more likely to get them replaced or cosmetically altered. And the opposite was true for non-war amputations like diabetes. And this makes sense because people with war-related amputations tend to be more active, and so they tend to break their prosthetics and in a way that they need to be replaced. Whereas people with diabetic amputations tend to be less active, and so they tend to have a small thing here or a small thing there that needs to be repaired or adjusted. And one of the big things about this, and the reason why this is important, is repairs and adjustments are cheap, replacements are expensive. And so this says even for the same cohort of amputees, so the same, even if you have 1,000 transtibial amputees, if they're war-related, it's going to be more expensive to provide prosthetics for them, but if they're diabetic, it's going to be cheaper. So this tells a lot about how the centers run and how they can budget in the future. One of the other things that we've done between November 2019 and July 2022 is we gathered broken prosthetic feet from the JJCDR. And most of these are locally manufactured. So if you look at this table, the string rubber and the sheet rubber, I'll explain what those are, were manufactured at the JJCDR. And we have exactly 100 of those. And then we have 22 which are made in Cambodia, or we didn't know where they were made. Now, the difference between the string rubber and the sheet rubber, if you look at this figure on the right, this one has lines that go up and down it. What they would do is there was a tire company that used to operate in Sri Lanka, and it used to have this cast off with basically fiber reinforced nylon rubber. And they put that on the bottom of the feet to make it stronger. But then when the company left, they just did nylon in covered rubber instead of with no fibers in it. This foot on the right, qualitatively, when we said this looks like it's going to make it mechanically weaker, and they're like, it does. They said, we think the ones on the right we would replace every 2 years. The ones on the left we have to replace every 3 months. So the reason why they use this material is because it's free, but obviously if you're replacing a part of the prosthetic every 3 months versus 2 years, that's more expensive. So we only focused on this string rubber feet is what we call them. And if you look at the bottom, this is quite worn out. And then you see a lot of wear over here, and you see a lot of wear over there. And this is different than what we would expect in high-income countries where people don't tend to wear down their feet. They tend to fracture and break their feet in that way. And the reason is because in the UK, everyone wears shoes, right? Whereas here, there's a big barefoot culture. And being barefoot and wearing sandals, which are really common here, lead to wear. This is particularly interesting because these feet, the Sach foot, is designed by the Red Cross, the ICRC, which is based in Switzerland. And so it's designed based on Western standards of wearing shoes. So these feet aren't actually designed to resist wear, which is the primary mode of failure here. So what we did is we created a method for quantifying the wear on the feet. And if you look at this foot on the left, the darker areas are higher wear and the lighter areas are lower wear. And so you see there's a lot of wear at the heel and the toe. And this has to do with heel strike and toe off during locomotion. And then you see there's a lot of wear on the outside of the foot. And that's because people tend to rock their feet back and forth. And then you see there's a lot of wear over here. And that's because there's this hard piece of plastic in there called the keel, which gives structural rigidity, and it's surrounded by rubber. And the keel, that's where the keel ends. And so there's a lot of bending moments around that part of the foot, which cause a lot of pressure, which causes the wear. And that's that patch that you see over there. And in this one, you can actually see part of the keel sticking out. It's pushed down so much over there. Then we also looked at the standard deviation and the coefficient of variation to figure out basically metrics of variation around this average, around this mean. And what we interpret this as is the mean is the areas of the foot that could be reinforced and redesigned. And so this, how do you make the foot stronger? but the variation tells us about individual differences in biomechanics, so differences in how the people are using their feet. So if we want to just in general make the foot stronger, we use the mean. If we want to make it stronger for that population, then we pay attention to the variation. So one of the big things that came out of the study is that after looking at 122 feet, not a single one of them fracturing, and all of them failing due to wear. This standard, the ISO 10328 standard, that is what these prosthetic feet were designed to. That's a safety standard that these prosthetic feet were designed to, and it has to do with fracture. These feet aren't fracturing, they're wearing, and so we should be designing them to a wear standard as well. So how appropriate are the ISO standards and for places like Sri Lanka? And from here, we got that if we're redesigning the foot, we should reduce the bending moments around the distal end of the heel, and we should probably try and have a more even pressure distribution on the bottom of the foot to stop these areas of high wear from occurring. And this got published last year in the Journal of Prosthetics and Orthotics, which is also, I think it's open access. If it's not and you would like a copy of it, please feel free to email me and I'll send it along. And so lastly, the last time we were here was in July 2022, which, as you guys will likely remember, that was quite an exciting time in Sri Lanka. And we did some field work. And so for the field work, we did, I'm going to go from bottom up, which I know makes no sense, but for some reason, that's how I made the slide. We did design workshops, which one was just with medical professionals and one was just lower limb amputees. We followed something called the double diamond approach to understand both problem ideation and problem solutions. And then we did surveys. We had hoped to get more than just about 20 people surveyed. We had hoped to get a couple hundred, but it was very difficult to get people to fill them out because of the conflicts that were at the time and the political instability. We did interviews with about 14 people, and we did ethnographic observation. That basically means we watched people in their workplaces and at their homes to figure out how they act and what they do. And this tells us different levels of evidence. The workshops tell us ideally what people would want. The surveys tell us how surveys and interviews tell us about how people perceive themselves, whereas the ethnographic observation tells us about what the people are actually doing. So if I asked you what your favorite drink was, you might say juice or coffee or tea. But then if I actually kept track of everything you drank during the day, I might find that 90% of the liquids is water, right? And so I would be like, oh, are you sure that your favorite drink is that? Because it seems like your favorite drink is actually water, because that's what you drink mostly. So people's perceptions of themselves and what they actually do often disagree. And this is good to have both because it tells us what the person wants and what they do. And so from this, the workshops, we held them separately, like I said, with medical professionals and amputees. And from the medical professional standpoint, we had prosthetists, medical doctors, and prosthetic and orthotic workers. And we found that like us, as engineers, they view the prosthetic as a technology. So they view it as its components. It has a foot, it has an ankle, it has a pylon, it has a, oh my God, socket. There we go, that's the last word I was looking for. And so it was very easy because the workshop was talking about feet. And so we could really focus the conversation on feet. But when we had the amputee workshop afterwards, they had a much more holistic view of the prosthetic because they didn't view it as the individual components that it was manufactured in. They saw it as an extension of their body. So we said, do you have any problems with your prosthetic feet? They said, yes. And we're like, okay, what problems do they have? And they're like, oh, it's a bit sore in my residual limb when I walk. We're like, and we would figure out that had something to do with the socket. And we're like, okay, but that's the socket. What about the foot, right? And they didn't view it as a separate thing. And they had a lot of trouble thinking about it that way. Because they're like, well, the foot gets the force and then that, and then that pushes the socket and then that gives me pain. So of course it's gonna be related to the foot. So one of the things that was really useful out of these workshops is not only to get from the medical professional side the type of information as engineers that we would often desire, but from the amputee workshop, we started thinking about the devices as a continuous thing, not multiple pieces put together, but as holistic, you can't break it apart, and it's an extension of the body. And then from the ethnography, interviews, and surveys, we found, not surprisingly, mobility is highly important to lower limb amputees. People travel, or it's important for them to travel to work and to go to shopping, and they want to be able to carry out their work. And then they also want to be able to ride motorbikes, push bikes, and drive tuk-tuks. And on the bottom left over here, you can see a picture. This was a transfemoral amputee who was riding a push bike, and I found that very impressive because I didn't know that they could do this. And so being able to get around is really important. And then stability related to that is also very important. So when they're walking, if they're carrying heavy loads, balance is very important. That's something that we know about from the literature. But what we also observe through the ethnography is that they arrange their environments in such ways that minimize their movement. So in the top left picture over here, you can see this guy in his shop. And he arranged everything in his shop in such a manner that he could stand in one spot and plant his prosthetic and then rotate around it. And so he used this prosthetic as a pivot. And we saw when a woman was cooking for us in our home, we saw her do the same thing. Her entire kitchen was arranged in a way that she could leave her prosthetic in one spot and just rotate. And so people really arrange their environments in a way to minimize the number of steps they're taking and maximize the balance, that once you get that one good balance position, you stay in that one position. Not surprisingly at all, capability was hugely important to these people. And so they have a desire for independence and they want to do what is right and what they're told to, but if you tell them to wear shoes, they're also going to do what they want and they're not going to wear shoes, right? And the capability was, and this is also related to the cultural differences, was absolutely astounding. So this guy, in this picture, he was a transtibial amputee, and you can see he was climbing the palm tree to do some toddy tapping, right? And I certainly couldn't climb a palm tree. So the fact that he, as a transtibial amputee, could do this, we just found astounding. But he's like, yeah, this is what I want to do, and this is part of my culture and who I am, so it's built into his actions. We also found some interesting cultural things. There's not a lot of Hindus where we're around, and that's not a very big religion. But we were talking to some of the Hindu women. We didn't know this, but they wear, as I'm sure you guys know, they wear their wedding rings on their middle toe. And the prosthetic feet, those toes are fused together, so they can't do it. And so the women started talking to us about how important it was as a source of identity to wear that ring. And if we just cut the toes, then they would become structurally unstable and the toe would break off and they'd lose the ring. So it's actually quite a complicated engineering problem to figure out how to enable the ring to be worn without breaking the structural rigidity of the foot. Also with this, the women wearing the saris, they talked about if they were transfemoral amputees, their knee joints would often rip the thin fabric of the sari. And so what they did is they took a rag and they wrapped it around the knee joint to stop that from happening. But once you're doing that, biomechanically it doesn't work. So they had to choose between wearing these beautiful saris and walking. And that's not a choice that they should have to make. And then there was a lot of people talking about kneeling and praying and such, but from this, we also found that a lot of times these prosthetics are non-inclusive. And this isn't surprising because most engineering products, no surprise, are designed for men, right? Because they're designed by men for men. And so they tend not to do what women want them to do. It was only a few years ago that the first female crash test dummy was made. And that was the reason why women have poorer health outcomes in car accidents than men, because their cars and car safety is designed for men. So similarly, there was a lot of unique problems that women had that men did not, but there were no unique problems that men had that women didn't. And so my PhD student, Gemma, she's really taken to this and she's focusing on using this to try and create some more inclusive designs for women. And so from this, we have these 4 lines of evidence. The published data told us that we need to look at full feet and we want to make them enable high levels of activity. The local prosthetic and orthotic records, again, we wanted to enable high activity with flexible functionality. And another thing that we saw is that people were, if we could enable home repair, then this would allow repairs to happen outside of the P&O center. From the broken prosthetics, we want to have distributed pressures, low bending moments, and flexibility in the materials that can be used. So that way, if it doesn't go from a foot lasting from 2 years to 3 months. And then from the field work, that mobility and stability are important, and amputees are highly capable, and that cultural flexibility and inclusiveness in design is incredibly important as well. And that means that the design that works for Northern Sri Lanka might not work for Southern Sri Lanka. Just like there's over 20 prosthetic feet for people in the UK, maybe there should be something similar within these countries as well, right? And so from there, my student Gemma, she's currently working on some designs, and we're tossing them back and forth. So unfortunately, I don't have those to share with you. But some of the stuff I'm working on, current and future work, we have a bunch of master student projects. So this ISO 10328 tester, like I told you before, that's about the fracture, that has to do with safety. And that machine costs £80,000. So a lot of universities in the UK can't buy them. And that, of course, that means a lot of places, prosthetic and orthotic charities, for example, in Sri Lanka, absolutely can't buy them. But when the JJCDR makes that transfer of material, when they're saying, oh, we can no longer get this one, we're going to substitute this one back in, that means they have no way to test whether or not what they're doing is structurally safe. So we want to create affordable testers that people can make within their local skill sets and local resources in places like Sri Lanka. Also, this prosthetic foot collection. We were just at the Sri Lankan School of Prosthetics and Orthotics yesterday, and all the P&O centers we're going to, I've asked people to save broken prosthetics for me. So from the 122, we got another 37 feet yesterday, and we're going to get lots more as we go. So I want to just keep on growing this collection, so that way we can continue to look at now variation within the country. I'm starting to talk to people about collecting them in the UK, so we can compare the UK to Sri Lanka. And I'm working with Southampton to look at volumetric changes in footwear. The Gordon Museum of Pathology is actually part of King's, where we are, and they have a whole section on replicas of body parts. So one of the things that's important for me from the anthropologist side is communication. So we're actually talking to them, and we're going to have a small section. We're going to have some of these prosthetics on display, and there's going to be stories of general stories of people that these came from. I think it's important to teach people from a young age about these issues. That way, when they go to university, they take these lessons with them and they have them in mind through their education. So I'm going to have 8 16-year-old kids working with my lab over the summer for a few weeks. And they're going to look at basically the inter and intra-observer error for this wear method that we developed. And then last April, my student Gemma had gotten a bunch of foot pressure data, and she's correlating it to see how foot pressure and foot wear are related to each other, to see is foot pressure distribution a good criteria for prosthetic foot design. Working with 2 startups, so one of them, two companies. One of them is a startup, and the other one's Vivo Barefoot, in this idea that we call feeling the ground. So the idea is that if you lost your foot, you can no longer feel the ground, and people trip and they slip. And this actually slipping, especially on the smooth concrete when it gets wet, was something that people talked about a lot in northern Sri Lanka. So we're talking about ways that you can improve sensing the ground under you. I have a student, Morgan Momo Alverson, who's going to be starting in October. And she, like me, has degrees in both engineering and anthropology. And so we're going to be focusing on I'm going to have her focus on some other regions in Sri Lanka, basically doing the same types of things that we've done before. And we've called it the farmer's foot, because that seems to be the biggest problem with these prosthetics, that they fail farmers. I'm working with Southampton on a project on prosthetics and archaeology, looking at them through time, because the oldest prosthetics are several thousand years old from ancient Egypt. And so it's kind of, what have people done? What knowledge have we lost? And how can that help them today? And we're looking at something related to flexible load-bearing sockets, and also doing some similar work with the surveys in interviews in Cambodia right now as well. And then, of course, like I said before, we're here to make collaborations and see what's going on. So if there's any ideas you guys have that seem to fit in with our stuff, or that don't fit in at all, but you're like, hey, maybe this will work, we're completely open to anything. So thank you so much for all your attention, guys, and for listening to this talk. If you have any questions, just feel free to ask.
So one question for Michael now. So your data set, I could see now the pediatric data. Usually when the baby is born, probably there might be some disorders.
Yes.
So did you consider those data? Because congenital disorders, there are different.
Yeah. So it's not labeled over here, but one of these is congenital disorders.
Right.
And yeah, so it's like, certain things like developmental disorders, clubfoot, even they have low oxygen at birth. can't remember what it is. But yeah, there's some of those that do end up with the amputation. It's with the children in particular because they tend to outgrow their prosthetics so quickly that, yeah, a lot of them don't come in, unfortunately. But this is one of the things that we're hoping that the Sri Lankan School of Prosthetic and Orthotics, we know have a data set as well. So we're talking to them yesterday and we're gonna circle, when we come to the end of our trip, we're circling back around because they're continuing to collect broken prosthetics for us. And it was down yesterday, unfortunately, but we're hoping it's gonna be up and that we can analyze their data as well. And I've already started talking about to Handicapped International and Candy as well. And we're gonna be visiting them about analyzing their data. So hopefully we can have a better understanding of regional variation within the country and how that affects some things like cause of amputation and age of amputation and such. Because it really does affect the cohorts and who you're designing for. One of the things that's particularly interesting is that a lot of them, there was a lot more male amputees than female amputees. And if there was somebody at the Red Cross who looked at data across 14 different countries, and she again found similar proportions actually of male to female amputees. And so she took it as, she interpreted the data as that women were not getting the service that they needed, that they just weren't coming in for it. But, so that could be the case, that the reason for this bias in the data. But if this is now the case across 15 countries, I'm not sure that that bias is true across all of these. I think it's because of war, right? And like just generally war amputees tend to be male. There are a lot of female war amputees, and especially within the Tamil Tigers, I've met quite a few female generals, and they have a lot. They're very powerful women, and I'm quite scared of them because they're quite powerful, but they, yeah, I think it's just, that's the reason why. So if you guys think of any questions later on, please feel free to email us. We're at King's, and you can just Google our names and find it, and we're very happy to talk about this. So thank you guys.
Yeah, I have one question from Nikki.
Okay.
Now your prosthetic design for the thumb, how many degrees of freedom you use in the design?
So in the right hand.
No, you can see it. So,
oh, sorry, for the online people.
No, this is from Zoom room.
Oh, okay.
So for the black hand, it had a motor to put in this way, and it was passive, so you can move it around. For the white hand, we have, I think it's 3 degrees of freedom with 2 motors coupled. So we can basically try and get that anatomical notion of the thumb with just 2 motors.
So the power is transmitted through a cable drive, right?
Yeah. So the underneath we have lots of motors underneath here. So I think there's 6 under here. Alright. And so yeah, 2 of these are being used for the thumb. So we've just got cables. You can just about see a couple of cables going through the center here, into the palm, and then you can see we have one here for the thumb, which goes up, pulls it in, and we have a second one here, so it connects this part. It's basically the muscle between these 2 parts that can pull it around. So the idea by the end of this person's PhD is they're going to have it in a compact, lightweight structure with plugging into the socket, and it can be tested by amputees.
So I have one question about the phalangeal joints. Like the phalangeal joints, they need to have different stiffness, right?
Yes, yeah.
So how did you achieve it?
So the way that we got the different stiffness is that you can see that where we have the joints here is very thin. So it's not very tall, and it's thinner in the width way as well. Whereas where we have kind of the part we don't want to flex, it's just thicker, bigger. So it's all printed with the same material. Printed at the same temperature. Is literally just the geometry of the material is how we get them applied to where we want it to be.
So how you use any kind of simulation or something to come up with the geometry? So
this has been done purely through experimental testing. So they printed off quite a few different fingers to work out roughly how it should be. They are going to do some finite element analysis to do some more refined designs. Now they've got kind of close to the area to try and optimize the design. So they will be doing some simulation design, but up until this point, it's just been experimental and used a lot of results from my previous students as well.
As I remember, you said that for the last 3 fingers, you are using a single actuator.
Yeah.
What if you remove one finger? It will be a 4-finger hand. So will that make a difference?
So probably not. So I think 4 fingers, you would still be able to do all the red patterns. The reason we put 5 in is just because it looks like a hand, and a lot of people prefer that cosmetically. The reason we have a single motive for the last 3 fingers is because most grip patterns we use for objects, these 3 fingers all move together. So there's no reason why these should move independently for the grip patterns, apart from like maybe a couple of obscure ones. But in day-to-day, like daily living activities, these 3 fingers move together.
Yeah, I have a question. Did you find any active prosthetics used in clothing part of it?
Sorry, say again?
Any active prosthetics used in it?
No, they only get passive prosthetics. And actually the Sri Lankan School of Prosthetics and Orthotics as well, they only give passive prosthetics right now. And it has a lot to do with where the funding is coming from. So the Sri Lankan School of Prosthetics and Orthotics is funded by the government. And the government's thing is, if it's cheaper, then that's what you're doing. And so they used to give single axis ankle joints, but they no longer do that. They just give the Sach foot. And in the north, in Jaffna, they manufacture their own prosthetics. And that's what
when it comes to knees.
So they use, again, passive. It's just a single axis joint that you can lock.
Do they manufacture it or they're borrowed from automotive?
So they, it's all Red Cross, ICRC designs.
ICRC.
Yeah. And so some of them, because that's not patented, there's a couple different people who manufacture that design, and one of them is in Cambodia. So one of the things they were talking about yesterday to us is they bought a bunch of them from Cambodia and they don't work well, so they're like, oh, so we're looking for a different supplier. And then I know that the Sri Lankan School of Prosthetics and Orthotics, they said they were a national something, which I can't remember the word now. But essentially they help distribute prosthetics to other centers within Sri Lanka that are government run. So it seems like any government run, at least non-military centers, are going to have the passive devices for the time being.
All of them are moving on.
Yeah, and it all just comes down to money. And even then, they don't give out upper limb prosthetics anymore. It's just lower limb that they give out.
You told about that customization with that ISO 10.
Yes.
Right? It's not going to be the case in here.
Yeah.
How are you going to address that?
So the ISO, like how to make the affordable tester, or yeah. So there's 2 types of tests that are done with the ISO 10328. One is the static and one is the dynamic. So static, you put 80, I forget what it is. I think it's like 60 or 80 kilograms you put on it. How far does it displace? So you could actually create just a metal box, right? Put the foot at the 10-degree angle it needs to be, pile up weights until it gets to what you need it to be. And then you have like a scale and an arrow, and is it above or below? So you could do something very simple like that. And that's the type of thing that anyone who has a metal workshop can then create. So I have a student that's working on creating that. And then the other one is going to be a bit more difficult because it's a dynamic tester. And so you have to hit, I think it's, one of them's 10 degrees and one of them's 20 degrees, I forget which, but it's the toe is like at a 10-degree angle and the heel is like at a 20-degree angle, or the other way around. And it has to be a certain load again. And you have to do it, thousands and thousands and thousands of times. So that one is a bit more difficult to get done. But so I'm thinking about it in 2 separate projects. One is relatively easy, and that one we can knock off. And then the other one's going to take a lot more time. But yeah, we need a lot of people that do control systems.
And the other thing is like, that is the ISO standard.
Yes.
Then when you are like, considering, say, like, you have to implement the thing in a very precise manner.
Yeah.
And, how to get the recognition, like, possible to get like a regional recognition for this, or the ISO, like regional
Oh, so instead of going to an ISO standard, go to a different standard that's like in your. So there's not a lot of standards in prosthetics and orthotics. So there's two ISO standards, the 10328 and there's the 22675 are the main ones, and they test in completely different ways, right? But the ISO 10328 is the one that's used in the UK, and the 22675 is the one used in Germany. And so Autobach, which they have a branch in Sri Lanka, I imagine would test towards the 22675. There's not really, besides that some labs have their own standards. Upper limb prosthetics, there's no standards other than lab standards. So like some of the stuff that we have, one of the things that, because like the wear being a big problem, I've started talking to some tribologists. I'm like, could we develop a wear standard for this to test it out? And it's starting from scratch because nothing exists. So we'll do it, and then if it works, it works. If it doesn't, then we try something else, and then that'll be the local standard. Right? Yeah.
So Mike, did you say that you are going to get some data from Candy?
Yeah, so that's what we're hoping to get from Handicapped International, yeah.
It's important because I think the preferences will differently change depending on the terrain. So Candy is a highly country of Sri Lanka.
Yeah.
So definitely the people different have different preferences.
Oh, absolutely. And that's the reason why we want the data, because we want to be able to show some of this stuff. And then, and so, yeah, like we did before, we started with the data and then we did some of the personal stuff to get much of it more. So that's the idea is, we start with the data and then we can show quantifiable differences in the demographics. And then it becomes easier to get some money to then do the next steps. But yeah, especially the elevation differences, and the Center for Handicapped International also does, like they'll go to Batacola and then do some work there, and they'll go there and do some work there. So their database will actually have some regional variation within it as well. That's why I'm like, I really, really want to work with you guys. They've given me some summative data, so they've given me like pie charts and bar graphs. I'm like, no, but I need the raw numbers, so that way I can do all these statistics on them and see these patterns. And I imagine it'll be different too here in Colombo, or in the Colombo area, right? That's where it's in Ragavan, is the Sri Lankan School of Prosthetics and Orthotics. And there's also, I forget what it's called, but there's one in Tengali, and I don't know if they have a digital database, but we're going to see them in a few days. So I know that there's the one in Gal, how I'm going to mispronounce the city name, Gali? Gal. There's one in Gal that it's only been around since 2016, but they only have paper records right now. So we could get it, but then we need to sit there for a month and transcribe everything. So it's not something we can do on this trip at least. But I have done that before, sitting there and transcribing records.
So I have one question. So it's regarding the prosthetic arm on the left.
Yeah.
So it's a tendon-driven, so it includes a tendon-driven mechanism.
Yeah, so my students signed that, yeah.
So how is it able to change the trajectory of the finger to grip a cylindrical object, and then again a pen or something that requires precision hand?
So a lot of it is how we control the hands. So there's some papers published about the different types of grasps and grip patterns that you have for different objects. So we can program the hand to move to different grip patterns, but a lot of it is to do with the fingers being under actuated and compliant. So because we have this new type of joint that's flexible, it can twist a little bit side to side, just like the human finger has a little bit of twist. So when an object's put there, it kind of morphs around the object. So in that sense, if you have the same grip pattern for two different objects that are completely different, it will morph around the object and really kind of grasp it, just like the human hand will. So it's all to do with the joints and the under actuation and compliance of the joint, really.
Thank you, guys.
Thank you.
So we'd like to thank Dr. Michael Berthaume and Dr. Nicola Bailey. Thank you very much, Mike and Nicola. So we will end the first visit of 2024. Thank you very much.
Thank you very much. Thank you.